Okay. So, good evening, everyone. So, my slide is visible to everyone. Is it visible to everyone?
Yes,
Yes,
sir.
Asis. Yeah. Okay. Thank you so much. So, today we have 12th class and 19th Feb. Okay. So, in the previous class, we discussed the three-phase half control rectifier control of the DC motor. So, we have to control the DC motor by the three-phase half control. Okay, and then we can discuss the DC regenerative switch diagram. Okay, and dual converter control of DC separately excited motor, and drawback of the rectifier, and finally chopper control separately excited DC motor. Okay, so these topics we already discussed in the previous class, and I got the one query from the ASIS. Okay, so that is around couple of the questions. So total 5 questions. Okay, so that question I will prepare the proper step by step notes and give the explanation in the next class. Apart from that, those questions, any more question from the any students? If no question, then we can start our the new topic. Okay. So today we will discuss the chopper control separately excited DC motor. Okay, so basically we have to use the chopper. Okay, then we will discuss the regenerative braking. Okay, there is a chopper feed regenerative braking. Okay, then motoring and regenerative braking of DC motor, and finally dynamic braking of the DC motor. Okay, so we will discuss today 4 topics. Okay, so just 1 minute. So somebody want to join the class. Okay. Yeah. So uh, chopper control of the separately excited DC motor. So in the last class we already discussed the, what is a chopper. So chopper is nothing but DC to DC converter, correct? So there is a buck converter, boost converter, cuck converter. Okay. So that is a it is a chopper. Okay. So we can say it is a DC to DC converter, and we have a DC motor. So by controlling of the chopper, we can control the speed of the DC motor. Okay. So let's first discuss the motoring operation. Okay. So in the last class, we already discussed this diagram. There is a supply voltage, and this is our transistor, otherwise thyristor, and this is a prevailing diode. Okay. And this condition is, we can see the motor, it is a RALANE. So transistor chopper control of separately excited motor, it is shown in the figure 1. Okay. So transistor, there is a TR is operated periodically because we have to give the firing pulses to operate this transistor. So we can say the alpha. Alpha is a firing pulses. Okay. With the period T and the remains of the for the duration T on. Okay. The present day chopper operate at a frequency that is a high enough to ensure the continuous conduction mode. Okay. So we can say nowadays we are operating the chopper to control the speed of the your DC motor. Okay. Yes. So waveform of the motor terminal voltage VA. Okay. So that is armature voltage and armature current for the continuous conduction are shown in figure 2. Okay. So we can say this is a on time period and this is a off time period. Okay. So this is a voltage across the switch. Okay. Voltage across the armature. Okay. So we can say the T on time period, and then this is a T off, and again there is a at time T, there is a on time period. Okay, so this is a voltage across armature. And what about the current? So we can say current is increase and then is a decrease during the off time period. Okay, so this is a simple voltage and current waveform of the armature. Okay, so during the T on and T off time period. Okay, so during the on period of the transistor 0 to T on, the motor terminal voltage is at 0. Okay, so we can say motor terminal voltage is equal to VA at 0 to T on. Okay, and for the T on to T off, voltage is a 0 volt. Okay, so from the figure you can see from 0 to t on, that is a voltage is a VA, and from 0 t on to t, not t off, t on to t, voltage is a 0 volt, and corresponding the current. Okay, so derivation we can say, suppose you have to apply the KVL for this for this loop, so we can say RA into IA. So current flowing in the resistor, there is RA into IA plus LA di by dt. Okay, and plus E is equal to V. Okay, so we can say for the KVL in this circuit, so once the circuit switch is closed, so we can say current is flowing in this circuit. It is a IARA plus LA di by dt plus E equal to V, and time period, that is a 0 to t on. Okay, this interval, the armature current increase from IA1 to IA2. Okay, so that is a current is increasing. We can say current is increasing like this. Okay, so we can say IA1, and this time period is a IA2. Okay, and then again is a close, off, on, off. Okay, increasing, decreasing is the armature current. Okay, so since the motor is connected to the source during this interval, it is called the duty interval. Okay, so 0 to t on time period is nothing but your duty interval. Okay, so at t equal to t on, TR is a off time period. Obvious, that is a, from this figure we can say t equal to t on, TR is a turn off time period. So motor current freewheeling through the diode DF, and the motor terminal voltage is 0 during the interval of T on to T off. Okay. So during the freewheeling diode, during the freewheeling operation, so that is your turn off time period of the transistor. Okay. So that in during that time, so the current is flowing in the through the freewheeling diode. Okay. And motor operation during this interval is known as a freewheeling interval. Okay, freewheeling interval during this operation, and what we can say, that is a, so we can write equation Ra plus La di by dt plus E is equal to 0, because now V is disconnected from the supply, so we can say V is equal to 0 during the T off time period. So this is a T off time period. Okay, so motor current decrease from IA2 to IA1 during this interval. So during the during T off time interval, motor current is decreasing from the higher level to lower value. Okay. So simple duty cycle we can say duty cycle, otherwise the duty ratio we can write duty interval divided by total time period. Okay. So duty interval is nothing but T on upon T. Okay, and then we can write the voltage equal to 1 by t, 0 to t on V into dt. Okay, so 0 to t on is nothing but, that is here t on by t is nothing but your del, correct? So we can write VA is equal to del V, because this thing is nothing but your delta, correct? So this thing is delta. Yeah, this thing is a delta, just one minute. Yeah, this thing is a delta, so we can write VA equal to delta into V. Okay, so what about the current? So armature current is equal to del V minus E upon RA, correct? So we can write this equation in the form of the VA minus back EMF voltage divided by RA. So VA is nothing but your delta V minus E divided by R. Correct? So VA is nothing but this value. Correct? So we can say IA equal to del V minus E upon RA. So from the fundamental equation of the DC motor, we can write omega m equal to delta V upon K minus RA upon K square into T. Okay. So this is your speed of the DC motor for the separately excited motor with respect to the delta, that is a duty interval. Okay, so omega m is equal to del V upon K minus RA upon K square into T. That is equation number 6. Yes. Now we have to discuss that is a regenerative braking. Okay, regenerative braking of the chopper feed separately excited DC motor. Okay, so that is a motoring mode and the regenerative braking. Correct. So motoring mode and braking mode. Okay. Yes. So regenerative braking, okay. So we can say the circuit diagram of the regenerative braking of DC motor. So this is supply voltage, okay. Then is a capacitor, okay. Then here is a diode, okay. Here is a transistor, and then is a motor. So we can say this regenerative braking is nothing but your boost converter. Okay, so we can say it is a boost converter. So previous one there is a buck converter and this one is a boost converter. Okay, so if you remember that boost converter, so this is a same diagram of boost converter, but what is the role of this capacitor? Capacitor is nothing but your filter, correct? So we can say that it is a uh, we can say that DC voltage is a ripple free voltage, correct? So this role of capacitor, it is reduce the ripple. So chopper control separately excited DC motor is shown in the figure 1. So this figure, transistor TR is operated periodically with period T, okay, and on period is a T on, okay. The waveform of the motor terminal voltage VA and armature current IA for the continuous conduction are shown in figure 2. Okay. So we can say this is your T off time period. This is T on. Because buck and boost both are just inversely proportional, correct? In the buck converter, you will get the less voltage, but in the boost converter, you will get the high voltage. So waveform is you can see in the T off time period, current is increasing, and during the T on time period current is decreasing, and again cycle is repeating. Okay, so this is a T on to T off, that is a T turn on time period, and 0 to T on, that is a turn off period. Okay, the usually the external inductor is added to increase the value of the LA. Okay, when TR is on and IA is increasing from IA1 to IA2, similar to the previous case, correct? The mechanical energy converted into the electrical energy by motor. Yes, the mechanical energy converted into the electrical energy by the motor. Now working as the generator. Correct? So this is a regenerative braking. So we can say whatever energy is stored in the electrical energy in the form of the inductor. Correct? So because inductor is an energy storage element. Correct? So while you brake the vehicle, so it will create the energy, correct? And that energy we can convert into electrical energy. And then we can say now our motor is working as a generator. Okay. So it means the mechanical energy converted into electrical energy by the motor now working as a generator. Partially increase the store magnetic energy in the armature circuit inductance, and the remainder is the dissipate armature resistor and the transistor. Okay. So most of the energy is stored in the form of the magnetic energy storage. Okay. Because we have an inductor. Okay. And remaining energy may be the waste in the form of the inductor. Otherwise, we can say in the form of the heat. Okay. So our target is as a research scholar, as a power electronics and drives engineer. Our target is we have to store the maximum energy, and we have to feed the maximum generated energy into the source. Okay. So when the TR is turned off, armature current flow to the diode D and source voltage V and reduce the from the IA2 to IA1. So just when we transistor is turned off, then remaining current is flow to the circuit. So there is a through diode. Okay. The store electromagnetic energy and the energy supplied by the machine is fed to the source. Yes, the interval 0 to t on is now called the energy store interval. Yes, while 0 to t on time period, we can say there is a energy storage interval because that time energy store in the inductor time. Inductor, okay, that element is an inductor. So that's why we can say 0 to t on time period, that is your energy storage interval. Okay. an interval t on to t, that is a duty interval. Okay. So while turn on the switch, that is your duty interval. So we can say this interval, that is your duty interval. Duty interval. Okay. So what is a duty interval? That is a t minus t on divided by t. That is your duty interval. Okay. So from this figure 2, so there is a waveform. From this waveform, we can say VA is what? There is a T on to T. So integration T on to T into V into dt. So what you will get? So you will get there is a delta V. Okay. So suppose you have to find out this area. So how we can find out this area? So integration 1 by T. So 1 by T is at the total time period. Okay. 1 by T integration starting point to ending point T on to T and total voltage, that is a V. Okay, so we can say VA equal to 1 by T into V VT on minus T. Okay, and T on minus T is nothing but your delta. Okay, so we can say VA is equal to delta V. Okay, so this is simple area. We have to find out the energy, otherwise we have to find out the total area. So we have to use the integration. Okay, and from the figure 1, so this circuit diagram, we can say I equal to E minus del V upon RA. So that is your total current flow in the circuit, that is I equal to E minus del V upon RA. And since IA has reverse, because now current is fed from the load to the supply voltage, correct? So we can say now current is flowing the reverse direction. In the previous case, during the motoring operation, current is flowing from the source to load. But now in the braking operation, current is flowing from the load to the source. So now we can say current is a reverse direction. So we have to take the negative direction. So we can say torque equal to minus K into IA. Okay. And from equation 3rd and 4th, we can write omega m equal to del V upon K minus RA upon K square into T. Okay. So in the form of the speed, so speed relation in the form of the delta, there is a duty interval for the boost converter. Otherwise, we can say the regenerative braking. The nature of the speed torque characteristic is so in the figure 3. Okay, so you can see on the y-axis that is omega m, that is a speed, and on the x-axis that is a time, a torque. Okay, so torque versus speed characteristic for the motoring as well as the regenerative braking. So we already know that is a speed torque characteristic for the separately excited DC motor is a straight line, correct? It is a straight line for the motoring operation. But for the regenerative braking, there is a just opposite of the motoring. So we can say we can extend this the line in the second quadrant, and that is your regenerative braking operation. Okay, and now there is a relation of the delta. Okay, so delta, you can see you can increase the delta value, so you will get the different uh, different value of the speed. Okay, so that is a delta value. Okay, so this is a speed torque characteristic during the regenerative braking. Okay, now there is a both case, there is a motoring and regenerative braking of the DC motor. Okay, so now we can say the suppose we have a motoring as well as the regenerative braking, then how it is a work. Okay, so we can say this is a buck converter. Okay, so first thing is the motoring, there is a buck converter. Regenerative braking, there is a boost converter, and now we can say motoring as well as the regenerative. So we can say sometimes we have to increase the voltage and sometimes we have to decrease the voltage. Otherwise, sometimes we have to feed the voltage to the motor, and sometimes we have to maybe take the voltage from the load. Okay, so there is a motoring and regenerative braking. So now we have to club the both things. Okay, there is a motoring as well as the regenerative, and we have to make the simple circuit, and we can cover the both things, that is a motoring as well as the regenerative braking. Okay, so this thing is nothing but your buck converter. Okay, so we can say the supply voltage here is a capacitor for the filter ripple filter voltage ripple filtration, and we have a two thyristor and connected with a two diode, and this is your motor. Okay, so this is your motor. Okay, so we can say we have a single leg but two switch. Okay, upper switch and lower switch. So we can say from 0 to delta t, there is a t on time period and this t off time period. Okay, so where we can operate the t on, so we can say t on time period is transistor 1 and the diode 1. Okay, so we can say current is flowing from here to here, here to here, this path, this path, and back to the this path. Okay, so that is your uh, just wait, somebody want to join the class. Yes, Manoj. Yes, Manoj, you are too late today. Yeah. So there is a yes, I was discuss about the yes motoring mode as well as the regenerative mode. Okay. Yeah. So chopper circuit of the figures 1 and 2 can be combined to get the two coordinate chopper of the figure 4. Yes, so that is a figure 1, that is a buck converter, and otherwise we can say the motoring operation. Okay, and figure 2, that is your regenerative braking, and then we can say it is your boost converter. So we can club the both figure 1 and figure 2, because in figure 1 we have a one switch and figure 2 we have a one more switch. So we can combine the both switch and total we have a two switch and total we have two diode. Okay, and we can make the one more circuit, and that is your Kirk converter. Okay, otherwise we can set a step up and step down converter. Okay, so we can do the both thing using this converter. Okay, so figure 4, which can provide the motoring and the regenerative braking operation in the forward direction. Okay, yes, transistor TR1 with the diode D1. So this is transistor TR1 and with the diode D1. From the chopper circuit is similar to the figure 1, and figure 1 is nothing but your buck converter, otherwise the motoring operation. Figure 1 is nothing but motoring operation, and therefore provide the control of the forward motoring operation. Correct? So it is a work as a, suppose you operate the transistor TR1 and diode D1, then we can say it is a motoring operation. Okay? And suppose you can operate transistor TR2 with the diode D2 from chopper circuit, it is similar to the figure 2, and figure 2 is nothing but your braking operation, correct? And therefore provide the control of the forward regenerative braking operation, correct? So you can see the current waveform. There is a starting from the negative because there is a braking current, correct? So it is a feed to the source. Okay, and then it is an increase once the TR1 is on, then it is an increase in positive direction, then again is decreasing, and after some time again is going to negative when you operate the transistor, second transistor. Okay, and then again is increasing. Okay, so one by one you have to operate the transistor diode. Okay, and that current is flowing the continuation. So sometime maybe the forward motoring and sometime maybe the reverse forward braking. Okay, so then we can say this step up and step down converter, that is operate in the both mode, that is a forward motoring as well as the forward braking operation. Yes, thus the motoring operation transistor TR1 is control, and for the braking operation transistor TR2 is control. Yes, for the motoring operation we can operate TR1 and diode, but diode is a not controllable device. Okay, so we can say diode we can use as a freewheeling. Okay, but for the braking operation we can operate the TR2. Okay, shifting to the control from TR1 and TR2, shift the operation from the motoring to the braking and vice versa. Okay. In the servo drive, where fast transition from the motoring to the braking and vice versa is required for the both TR1 and TR2 control at a time. Okay. So in the sometime maybe we can operate the both transistor TR1 and TR2 at a time to get the very quick response. Okay. So we have to operate the both transistor TR1 and TR2 at a time. Okay. Yeah. Yes. So in the period of T, so in the period of T, so we can say we have to operate the transistor. We have to operate the transistor TR1. TR1 is the given at the gate drive from the 0 to delta T, and TR2 is given gate driver delta T to T. Okay, and delta T is nothing but your duty interval. Okay, where delta is a duty ratio for TR1. Okay, and therefore from 0 to delta T, motor is connected to the source either to the TR1 or maybe the D2, depending on the whether the motor current IA is positive or negative. Okay. So depend on your operation, you have to operate the TR1, otherwise TR2. Okay, and you have to complete the cycle, because once the cycle is complete, once the circuit is complete, not the cycle, once the circuit is complete, then current will flow in the motor. Correct. So suppose you want to operate your motor as a motoring mode, then we have to operate the TR1 and D1. Okay, and suppose you want to operate your motor in the generating mode, that is a regenerative braking. Okay, then we can say we have to operate the remaining transistor and diode. Okay, since V greater than E during this period, the rate of change of current is always the positive. Yes, supply voltage is always the more than to the braking volt back EMF voltage, then we can say it is always positive. Similar to the delta T to T, motor armature is short circuit either to the D1 to TR2. Okay. Depending on whether IA is positive or negative, and during this period, change of the current is the always negative, then we can say it is a forward braking. So we can say forward motoring, forward braking, reverse motoring, and reverse braking operation. Correct? We have a four quadrant. Correct. So we can say this is a TR1 and here is a TR2. Okay. So one by one we have to operate the transistor in the diode. So now we can write the equation for the in the form of the voltage and the delta. Okay. So motor terminal voltage and the current waveform is shown in figure 4b. Okay. So this is a figure B and this is a figure A. Okay. So from figure B, we can say VA equal to delta V. So we can say VA is equal to delta V. Okay. And then we can write I equal to delta V minus E upon RA. Okay. So this is nothing but V equal to IR. Okay. So we can write I equal to V upon R. Correct. And V is nothing but delta V minus back EMF. So we can say current flowing the circuit, that is a delta V minus E upon RA. Okay. Yes, that is above equation. There is equation number 1 and 2. One that is a delta V and second one that is a IA. Suggest the motoring operation, there is a positive IA take place when delta greater than E by V. Yes. But for the regenerative braking operation take place when delta less than E by V and current that is a negative. Correct? And transition from the motoring to braking and vice versa occur delta equal to E by E. Okay. So for the motoring, yes, of course, current is positive, and for the braking, there is a current is negative. Okay. From the above equation are similar to those obtained for the chopper. There is a figure 1 and therefore given the same numbers. Okay. Yeah. So till now, any confusion that there is a motoring and regenerative braking of the DC motor? So till now, we discussed the separate operation. There is a motoring operation, and then regenerative braking operation, and then third concept, that is a combine. So we have to combine the motoring as well as the braking, and then we have to see the waveform and which type of which converter we have to operate. Not converter, which switch we have to operate. Correct? Yeah. So last topic, that is a dynamic braking of the DC motor. Okay. Again, that is a braking, but we can say that is a dynamic braking. Okay. So dynamic braking, again we have to discuss the same circuit. Okay. So we can say dynamic braking. So any idea what is a dynamic braking? So if you remember the dynamic braking, any idea to anyone? Yes, Asis, any idea about dynamic braking? Yeah, Asis
I
is
think,
not
sir,
there.
we use that resistance to drop the speed of the motor.
Yes, correct. So we have to remove the we have to disconnect the supply voltage. Okay. So in the previous case, here is a supply voltage. This is a V. But this is your dynamic braking. So what we have to do? So we have to remove this voltage source. We have to remove this voltage source, and we have to connect one load register. Okay, otherwise we can say the braking register. So we can restore the all the energy to the register, braking register. Okay, so register is nothing but we can say it is oppose the current, correct? So ultimately we have to give the braking operation, correct? So we have to connect the additional register, that is a braking register. Okay, so dynamic braking circuit, and it is waveform is shown in figure 1 and 2. So this is a circuit diagram of the dynamic braking. So there is a braking resistor RB, transistor, and then is a remaining part, that is your motor. Correct? So during the interval 0 to t on, during the interval there is a 0 to t on, IA is increasing from IA to I2. So you can see this figure. So current is increasing. Okay. Then once the U transistor is turned off, then again transistor current is decreasing and again is increasing. Okay. So part of generated energy is stored in the inductance and rest is dissipated in the RA and TR. Okay. So you connected the register, that is the RB. Corrected. So that is the rest of the energy is dissipated in the RB. So during the interval T on to T, IA is decreasing from the IA2 to IA1. Okay, so this is IA1, not IA2. So this is IA1, IA2 to IA1. Okay, so during the interval T on to T, IA is decreasing from the IA2 to IA1. Okay, the energies generated and stored in the inductance are dissipated in the braking register. There is a RB, RA, and diode D. Okay, so whatever energy you generated and whatever energy is stored in the inductor, and that is dissipated by the braking register, that is a RB, and that we already connected in the circuit. Okay, and another element, that is a RA and the diode. Okay. So transistor TR controls the magnitude of the energy dissipated in the RB, and therefore the control its effective value. Okay, so we can say yes, transistor we can control easily. Okay, so transistor TR control the magnitude of the energy dissipated in the RB and therefore control the effective value. Okay, if IA is assumed to be the ripple-less DC. Okay, so suppose current is a ripple-less, there is a no ripple in the circuit, no ripple in the current, then we can say energy consumed En by Rb during the cycle of the chopper operation. Okay, it means suppose IA is assumed to be the rippleless, so we can say the energy consumed, there is the En by the RB during the cycle of the chopper is IEN is equal to IA square into RB T minus T on time period. Okay, and RB that is your braking register and EN that is your energy. Okay, so that is energy is nothing but your IA square into RB that is a braking register into T minus T on time period. Okay. So average power consumed by RB. So how we can find out the power? So power is nothing but En upon T, correct? So P equal to En upon T. So we can put the value of En, there is Ia by R Ia square into RB 1 minus del. Okay. So there is a value of the E, correct? Okay. And effective value of RB, that is what is the value of RB? So we can say the RB effective value of the RB, that is the P upon Ia square. Okay. So we can say RB minus 1 upon delta. So suppose you put the value of P, then we can say Ia is cancel out. So remaining part is a RB 1 minus del. Well, del that is your duty interval. Okay. So, yes, so this is a last topic. There is a dynamic braking of the DC motor. Any confusion from the today's class? Yeah. So in the today's class, we discussed the chopper control, separately excited DC motor, regenerative braking, and then motoring and regenerative braking. So, and finally, we can say the dynamic braking. And dynamic braking is nothing but we have to disconnect the voltage, and we have to connect the register braking register. Okay, and then we can say it is a dynamic braking. So, any confusion, any doubts from the today's class? Yes, student. No confusion. Okay. Then okay, then we can close this today's class, and it is my humble request, so please submit your lab 1. Okay, so by end
Excuse me,
of the
sir.
yes, Madhusudan.
Sir, in this lab, which curve is should be plotted? Torque versus time and speed versus time, or
Torque versus time, speed versus torque, and voltage and current waveform.
okay, B versus IA, sir.
Yes. So that is a
Okay.
separate waveform. So voltage versus time, current versus time, and speed versus torque. So VI characteristic and speed torque characteristic.
But generally, in case of DC motors, N versus IA and N versus T and uh, N versus T and T versus IA. These graphs are plotted. No?
So that is a depend on the analysis. So suppose you want to analysis the current versus the voltage. So that is up to you. Suppose you want to analysis the current versus torque. Okay, yeah, current versus speed. So that is up to you. So
Okay.
suppose you have a waveform of the voltage and current, and you have a voltage of the waveform of the speed, then you can get the relation. So that is up to you.
That means armature voltage versus armature current, sir.
Yes.
Okay, okay, sir.
So I
Thank you.
want the 5 waveform. First waveform, that is armature current. So on the y-axis that is armature current, and on the x-axis that is a time. Okay. Second
Okay,
waveform, that is a armature current on the y-axis, and on the x-axis that is a time. Third waveform, that is on the y-axis, that is a speed, and on the x-axis that is a time. And fourth one, that is on the y-axis torque, and the x-axis speed. And fifth one, that is the torque versus speed. So I want these 5 waveforms. Got it?
Okay, sure, sir. And
Yes.
load is to model the DC motor. Load is RLE load is included, sir.
Yes, RL load is sufficient.
Okay, sure, sir.
Okay.
Okay, thanks, sir.
Yeah. Any other query?
No, sir, it's fine.
Okay. So Ashish, so please send me your question, huh? So I will make the proper notes and then maybe I will discuss in the next class. Otherwise, maybe the I will discuss with you. Okay.
Sir, when are you planning to come to Nepal?
Ah, just 1 minute.